Got a new video for you, AP Calculus. This is a high alert AP type test question section. All right, it's very much saturated in abstract. You gotta know your stuff, thinking about the whole chapter. So you're going to be given a graph. It'll either be the graph of the derivative, which this first example is, or the graph of the original function. You need to be able to talk about it in terms of inflection points, maximum, minimum values, where are the intervals of increasing, decreasing, concave up, concave down. Maybe even talk about what's the first derivative look like for a specific point, what's the second derivative, can we compare 2 points, their values. There's a lot going on in this section. I'm going to do my best to explain it with 3 different examples. Hopefully you guys will come away with this with a lot of new knowledge. Okay, so given the derivative graph, we're supposed to be able to extract all this different information. Where are the inflection points, etc., etc. You see the list right there. So what we need to do is get a firm grasp on what this means. So when we get a derivative, okay, think about like a normal situation. All right, let's pretend like we're talking about an actual equation. Well, you know what? Here, let's keep it anonymous. Let's just keep it anonymous. How would you find, say, the intervals of increasing and decreasing for f of x? Yeah? Well, for these two, you'd say, well, I need to find the derivative, set it equal to 0, and then set up the intervals, test them. If your derivative is greater than 0, it's increasing. If it's less than 0, it's decreasing. So, I've got the derivative graph right here. Where does it equal 0? Here, 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 and there. Where is the derivative greater than 0? Where is the derivative above the x-axis? Where is the curve above the x-axis? That's where it's increasing. So we are increasing wherever you're above the x-axis. So the function increasing, 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 increasing stops for a moment. Increasing, 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 increasing. And then over here it picks back up, increasing, increasing, increasing. So the intervals of increasing for this function, and we're just going to pretend like this continues on to negative infinity and that this continues on to positive infinity. Your intervals of increasing are going to be negative infinity to not just a, like it's increasing, it takes like a little break at a and then it continues increasing beyond that. For negative infinity to the x value c. Okay? We're going to put a bracket there. Then we're going to go from I to infinity. Those are the intervals where f of x is increasing. Decreasing, it's just below the x-axis. So the function is decreasing, 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 decreasing. So, sorry if you didn't see that because of the brightness. It's decreasing along this entire stretch. So from C to I, the function is decreasing. All right, so we've checked those off the list. I think these kind of go in tandem with one another because what's happening? The places where it switches from increasing to decreasing are the places where it switches from increasing to decreasing are the maximum values. The minimum values are where it switches from decreasing to increasing. Okay, so where do we go from increasing to decreasing? Well, it's increasing until C, then it decreases at C. So it looks like letter C, everything above the x-axis is positive, which means it's increasing. Everything below the x-axis is negative, which means it's decreasing. So at point C, it switches from increasing to decreasing. So the zeros of the derivative are significant. The places where it changes from plus to minus are always max values, relative max values. And that's the only zero where it switches from plus to minus. This switches from plus to plus. That's not a switch at all. This goes from negative to negative. Also not a switch at all. And then you guys can probably see what's going on here. From decreasing to increasing, it's negative for my derivative to positive for my derivative. So decreasing to increasing at I. So I is a relative min. I is a relative min. C is a relative max x value. Wow. Okay. Now, I'm going to erase everything I've marked up here so we can talk about the second derivative. And why? Because concavity is all about the second derivative. So, the derivative is what's given to us. We have to start talking about the derivative of this function right here. The derivative of the derivative is going to inform concavity. Sorry, I said that weird. So what does the derivative look like? Well, the derivative of a function are the slopes of all the tangent lines that can be drawn on the function. So f double prime is informed by think of the tangent lines for f prime. Or think about this as an original function. Where is it decreasing? Because where this function decreases, the f prime, you're going to have derivative stuff to work with. So all the slopes of the tangent line here are negative. So from negative infinity to a, the slopes of your tangent lines of the derivative are negative, which means it's concave down where all the slopes of the tangent lines are negative, or where this function appears to be decreasing. So from negative infinity to a, it's concave down. From b to d, it's concave down. These are negative slopes of tangent lines from B to D. From F to H, it's also concave down. It's concave up from A to B. Because the derivative is increasing from A to B. From D to F, it's also increasing. And then from H, we'll just assume to infinity it's going to be increasing forever. All right. So I get it right away. This is super tricky. But we've taken care of concavity. The last thing are the inflection points. The inflection points are where you change from concave down to concave up and vice versa. So where does it change from concave up to down? Well, at A, it went from concave down to concave up. And then B went from concave up to concave down. And then D went from concave down to concave up. And then F, concave down to concave up. Or vice versa. Or, sorry, switch it. Up to down. You see what's happening? It's like all the min and max values of the derivative are the inflection points. Whoa. Okay, so A, B, anytime it switches from decreasing to increasing on the derivative, that's when you get an inflection point. F, and then H. All right. That's pretty heavy stuff. I'm tempted to just end the video right here and then make a new one with the next few, but I kind of want to just get this video over with. So, we'll have lots to talk about in our Zoom meeting tomorrow, right? Number 2. We're switching gears totally now. This is the graph of an original function, not the derivative. You're given g of x. The question is, can you talk about the derivative and the second derivative at each of these points? Determine the sign. So it's basically, is it positive or is it negative? So what I'm going to do here is, I've got A, B, C, D, E, F. I think I meant to do another one here, but just forget it. Yeah, forget it. Well, no, don't forget it. Let's A, B, C, D, E, F, G. All right, what we're doing here is determining, all right, is our derivative positive, negative, or 0 at that point? So take a look at A. A, if this is the original, then this right here would be the slope of the tangent line at A. It goes from decreasing function to increasing function. The first derivative equals 0 at that spot. Okay, it's not the derivative of this function right here, right? I'm not giving you a graph of the derivative. I'm giving you a graph of the original. And these little bumps down here are the max and min values where the slope of the tangent line is horizontal. What's the second derivative look like? Well, the second derivative is totally related to concavity. Concavity means holding water up or pushing it down. G of x, clearly holding water up. A is going to be greater than 0 right here for the second derivative. So you see where we're going with this? B, the slope of the tangent line is up and over, which means it's a positive derivative. So this one's going to be greater than 0. The second derivative. Now this is kind of tricky because sometimes it's harder to see where concavity changes. It seems like it's holding water up, holding water up, holding water up, but then here it's pushing it down, pushing it down. You've got a difference that seems to come to a head right here. It's probably safe to say that this is about 0. So it's an inflection point. Yeah, this is where the inflection points exist, where you change from concave up to concave down. Let's look at G now. G is just the opposite. The slope of the tangent line, instead of yielding a min value, yields a max value, but that still means that the horizontal tangent line's in place. Sorry, we're talking about G now. I know, I messed the whole sequence up. Concave down. Second derivative is negative. All right. Why don't you guys pause the video and try C, D, E, F on your own? Okay, let's see what you got. C, the slope of the tangent line is certainly negative, so we're going to say dy dx is going to be less than 0 on that end. The concavity, it's kind of hard to determine whether or not the concavity shifts here or here. I'm just going to make a decision and say the concavity is still down right there. All I know is that both of these can't be inflection points. So if you said equal to 0 on both of these, we definitely can't have that. D, a negative derivative, so the first derivative is less than 0. We're going to say this is the point at which inflection shifts. So concavity shifts from down to up right at D. Which means the second derivative equals 0. E, it's one of those bottom feeders. It's going to have the exact same situation as A. A and E are identical. Derivative is 0. Second derivative is concave up greater than 0. And then F, concavity is still up, and the slope of the tangent line is up. So it's kind of like concave up forever beyond that. So the first derivative, it's a positive slope, positive tangent line. The second derivative, concave up, is also positive. All right, here's my last example. What happens when you, okay, so we're back to the derivative. Sorry, that was kind of abrupt. We're back to the derivative. How can we compare original values to one another if all we have is the derivative graph? Not only that, but can we compare the derivatives and the second derivatives to 0 as well? So let's get to it. Point C versus D. We're basically saying, hey, who's bigger at F? Is the function F bigger at x equals C or bigger at x equals D? And here's how you can think about this. Pretend like you're the function F. Okay? So, there we go. I am now function F. I'm increasing, I'm increasing, I'm increasing, I'm increasing, I'm increasing, I'm increasing in value, still increasing in value, still increasing in value. Wait. I'm increasing again. Increasing, 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 increasing. Still increasing, still increasing, still increasing. Why was I increasing that whole time? Because I was above the x-axis the whole time. So from point C to point D, this derivative, okay, is still above the x-axis, which means the function's value continues to increase. So the function f of C is less than f of D because it keeps getting bigger to get to D. Let's think of D versus F. Okay, I'm at D. Yes. Whoa, I'm decreasing. Oh no, I'm decreasing. I'm decreasing. I'm decreasing. I get to F. F of D is bigger than F of F because it was decreasing from x equals D to x equals F. It's not decreasing because the function's going down. It's decreasing because the function's below the x-axis. It's a negative f prime, or in this case, h prime. Interval of decreasing below here. J versus K. Where's J? Okay, I'm decreasing, still decreasing. So J is bigger than K. Or f of J is bigger than f of K. K versus L. I'm decreasing. Okay. So f of K is bigger than f of L. So hopefully that was enlightening. You guys are like, you kind of get what's going on. You can always talk about points with respect to one another if you're given the graph of the derivative and you know firmly where it's above the axis and where it's below the x-axis. So now f prime at C. So f prime at c. Here is f prime at c. Sorry, I should have put h prime. That was my bad. I mixed them up. This is the graph of x prime. At c, the y value is 1, 2, 3. Is that greater than 0? Yes, it is. That's all you needed to do. At d, the y value is 0. So f prime at d equals 0. Here's another one. What's the second derivative at d? Well, the second derivative would be informed by the slopes of the tangent lines to f prime. The slope of the tangent line at that point would be a negative number, which means the second derivative is negative. I know what a lot of you guys are thinking. Doesn't it look like an inflection point? Yeah, it does look like an inflection point. But the inflection point of what graph? That'd be an inflection point of f prime, not of f. Remember, the inflection points when you're given the graph of the derivative are these babies right here. The max and min values of f prime are the inflection points of the original. All right, which is exactly what this last one is. F is an inflection point. Inflection points are where the second derivative equals 0, changing from concave down to concave up or vice versa. All right, I would expect you guys to have a ton of questions on this. Maybe even just a re-explanation in person, or at least one in which you can get immediate feedback with your questions. So good luck to you. And yeah, I hope we can like push through this assignment with some success. So thanks for watching.